here's the key to your test review. So when we start graphing over here, we're going to be graphing exponentials and logs. So you want to make sure that you have right in your mind which one looks like what. So far we have exponentials that we're going to have a little graph of, and we're going to have a log that we're going to have a little graph of. And so these are just one version of the parent functions, right? So for the exponentials, the parent functions all go through 0, 1, and the logs all go through 1, 0. And then the graphs themselves look something like this and something like this, where with the exponential, I have a horizontal asymptote, and with the log, I have a vertical asymptote. Okay. The only one that we actually wrote down a little t-chart for was the logs. It's fine to write it down for the exponentials. I might do the first one like that. Just make sure you're not getting them flipped around. There's a reason that we wrote them down for the logs and not for any of the other parent functions we did, just because it's easy to get that stuff backwards. So we're going to start with this. This is an exponential, so this is what the parent function looks like if the base is greater than 1, but this is 1/3, so it really goes like this. But I still have a horizontal asymptote, which is the important thing to keep in mind here. So with these, the first thing you want to do is write down what your parent function is, just so you can wrap your mind around it. We've got f of x equals 1/3 to the x power. Notice that my fraction is in parentheses, otherwise it's just 1 to the x power. And then I need to write down my transformations. So this negative here is going to be a reflection in the x-axis. 1/3 is my base. That -1 means I'm going to translate right 1, and then that means I'm going up 4. Right. Now my asymptote is horizontal because this is an exponential, and so what affects the placement of that, it's for the parent function, it's here at y equals 0, but if I have a vertical translation, that changes my asymptote, so it's here at y equals 4. First thing I graph, so it can also be the first thing I write down. So then I got to think about my anchor points. Now when we did these, we didn't write anything down, we just said, all right, well they all go through 0, 1. Okay, so that's my first anchor point there. And then I'm going to reflect that in the x-axis, which brings it down here. Translate to the right 1 and up 1, 2, 3, 4. When x is 1 for my parent function, y is 1/3, just right about there. I reflect it in the x-axis, move to the right 1, and up 1, 2, 3, 4. Then when x is -1, y is 3. So I reflect that in the x-axis, move to the right 1, and up 4. Okay. So I have 3 points plotted. This is very important. You have to have at least 3 points plotted. If those 3 points that are from your anchor points do not include the y-intercept, then you have to go find that and include that and get a 4th point. This one here, however, includes it. So I can just sketch that in. Looks something like this. Now, if you wanted to write down the parent function t-chart just so you can make sure that you get your points right, that's fine. But since this is an exponential, I'm not choosing numbers for y. That wouldn't make any sense. I need to choose numbers for x. So that's -1, 0, and 1. So that -1 was at 3, 0, 1, 1/3. That's what I used over here when I did it. I just didn't have it written down first, because hopefully you don't need to. That's why we do this. We do it for the logs, though, because it's easy to get it backwards. Okay, so my domain for every exponential is going to be -infinity to infinity. The range is what's going to change. This one goes from -infinity to 4. My y-intercept is at 0, 1. It's increasing the entire time, which means it's not decreasing at all. As x approaches infinity, f of x approaches 4, and as x approaches -infinity, f of x approaches -infinity. All right, so let's look at the next one. This is another exponential. So I write down my parent function. My parent function is f of x equals e to the x power. Okay, so I'll write down my little t-chart here so we can make sure we got this straight. -1, 0, and 1. That's what I'm going to choose for x every time. So when x is -1, that means this is going to be 1 over e, which is about 0.36. 0, it's at 1, and 1, it's at about 2.7. Now, the only reason I even write those down or use them is just because we're estimating on the graph. I am not ever going to use 0.36 or 2.7 in something I'm actually calculating. If I needed the exact decimals or whatever, I'd be using a calculator for that, but we don't have to get that close on these little graphs here. So then my transformations. This 2/3 is out front here, so this is a vertical compression by a factor of 2/3. Then this 2 right here is up in that exponent, so that is a horizontal compression factor 1/2, and then I translate right 1 and down 5. Okay, so it's another exponential, which means that my asymptote is horizontal, and this is the part that affects that. So I go to -5. This is where my asymptote is. And can also go ahead and do y equals -5. So my anchor points, when x is -1, y is about 0.36. Then I have a vertical compression by a factor of 2/3. So that 0.36, if I divide that by 3, that's about 0.12, and then multiply it by 2, it's about 0.24, so I'm about 1/4, I didn't really go anywhere. And then horizontal compression by a factor of 1/2 ends up right here. I translate to the right 1, and down 1, 2, 3, 4, 5. So when I'm at 0, I'm at 1. I have a vertical compression by a factor of 2/3, so I'm here at 2/3. Horizontal compression doesn't do anything when I'm on this axis. I move to the right 1 and down 1, 2, 3, 4, 5. Then when I'm at 1, I'm at about 2.7. So vertical compression by a factor of 3. So 2.7, think about, I'm going to have to 2.7 times 2/3 basically. So I'm going to divide by 3 and multiply by 2. So that 2.7 is like 27. Well, that divided by 3 is 9. So I'm at 0.9. Then I double that and I'm at 1.8. So I'm about right here. Horizontal compression by a factor of 1/2. Move to the right 1 and down 1, 2, 3, 4, 5. Okay, so those are my 3 points. They're really close together. What I don't have right here is my y-intercept, so I need to find that. My y-intercept is what I get when x is 0. So that'd be 2/3 times e to the 2, and then 0 minus 1 is -1, so it's really e to the -2 power minus 5. Well, nothing else I can do with that. Okay, that is equal to y. That is the y value of my y-intercept. It's 0, and then 2/3 e to the -2 minus 5 power. Okay. And I'm not even going to, I mean, I don't know what that is. I could probably come up with an estimate, but it's really not even important. So it's going to be about right there. It's the only place it can be. So I can draw this in. It looks something like that. Okay. Then my domain, -infinity to infinity. My range, -5 to infinity. Increasing, -infinity to infinity. Decreasing is none. As x approaches infinity, f of x approaches infinity. As x approaches -infinity, f of x approaches -5. Okay, let's look at this third one. So I'm going to first write my parent function, still an exponential. So f of x is equal to 2 to the x power. My transformations, I have a vertical stretch, a factor of 3. This negative is going to be a reflection in the y-axis. And then I'm going to translate left 2, and down 6. So I have a horizontal asymptote, go down 6, so 1, 2, 3, 4, 5, 6, right here. So y equals -6. My anchor points, so since I have 2 to the x, when x is -1, y would be 1/2. So I'm not going to write down the chart because I don't think we need to, but if you need to, that's fine. Then I have a vertical stretch by a factor of 3. So that 1/2 gets multiplied by 3, which gives me 3/2, which is like 1/2. I reflect in the y-axis, so it ends up over here. I go to the left 2, and then down 1, 2, 3, 4, 5, 6. When x is 0, y is 1. Vertical stretch by a factor of 3, so now my y value is 3. I reflect in the y-axis, which means I go nowhere. Go to the left 2, and down 1, 2, 3, 4, 5, 6. I didn't mean to actually make a point there. Okay, so then when x is 1, y is 2. So I'm here. Vertical stretch by a factor of 3, so my y value becomes 6. I reflect in the y-axis, and then go to the left 2 and down 6. 1, 2, 3, 4, 5, 6. Okay, so I have these 3 points. All right, so that point is totally wrong because when I reflected, I made stuff up. So I'm going to backtrack on that one. I think I ended up at x equals 2 at some point. So when x is 1, y is 2. Vertical stretch by a factor of 3 makes it 6. Then up here, I reflect on the y-axis, go to the left 2 and down 1, 2, 3, 4, 5, 6. And that makes a lot more sense. Okay, so what I'm missing here is my y-intercept. So that's when when x is 0. So I get 3 times 2 to the -2 power minus 6. So 2 to the -2 power is 1/4. So this gives me 3 times 1/4 minus 6. So that's 3/4 minus 6, which would be -5 1/4. And this is one of the very few times where a mixed number is fine. Improper fraction is fine too. So this is 0, -5 1/4. So I go to 0, -5 1/4, and I'm about right there. So then I can draw this in. It'll look something like that. Okay, so my domain for the exponentials is always -infinity to infinity. My range goes from -6 to infinity. I'm increasing none, and I'm decreasing throughout the whole interval. As x approaches infinity, f of x approaches -6. And as x approaches -infinity, f of x approaches infinity. Okay. So now we're going to graph some logs. So remember that the parent function for the log that we talked about on the front, go through x equals 1, looks something like this, and you have an asymptote here at x equals 0. Okay. So in this case, when I write down the parent function, I'm going to write it down in exponential form. It's still the parent function. I'm not changing this to an exponential equation because this is going to end up being 3 to the y equals x. So it's the same thing. This is not the inverse of this. It wouldn't be unless I switched x and y. So this is why I want to write my little table down, because now I'm choosing numbers for y. So -1, 0, and 1. And since we're always choosing numbers for x, it's easy to get it backwards. So when y is -1, x is 1/3. This would be 1, and this would be 3. My transformations, I just translate left 4 and down 2. So for these, my asymptote is vertical. So what changes my asymptote is the horizontal shifts. So since I go to the left 4, 1, 2, 3, 4, this is my asymptote. And then I start with these points. When I'm at x is 1/3, y is -1. And then I'm going to go to the left 4, 1, 2, 3, 4, and down 2. So I end up right there. Then when x is 1, y is 0. Go left 4, 1, 2, 3, 4, and down 2. All right, so then when x is 3, y is 1. Go to left 4 and down 2. So what I'm missing is my x-intercept, because I want the x-intercepts from the logs. So x-intercept I get when y is 0, so 0 equals the log base 3 of x plus 4 minus 2. So I'm going to add 2 to both sides, and I get 2 equals log base 3 of x plus 4. So now I rewrite that in an exponential, and I get 3 squared equals x plus 4. So 9 equals x plus 4, so x equals 5. So my x-intercept is going to be 5, 0. So 1, 2, 3, 4, 5, 0. My asymptote is at x equals -4. And I can draw this in. Looks like that. So my domain is affected by my horizontal shifts. So I'm going from -4 to infinity. My range for all the logs is -infinity to infinity. It's increasing the whole time, so that's from -4 to infinity, which means it's not decreasing at all. As x approaches infinity, f of x approaches infinity. As x gets as small as it possibly can, y is approaching -infinity. Okay, good. All right, so let's look at the next one. So I'm going to rewrite this in exponential form. My parent function is going to be e to the y power equals x. So I write down my little table here, -1, 0, and 1. So this would be about 0.36, 1, and about 2.7. This 7/4 is going to be a vertical stretch by a factor of 7/4. That negative is going to reflect in the y-axis. And then that 3 is going to translate down 3. So I have a vertical asymptote, which does not get affected. I don't have a translation left or right, so it stays here at x equals 0. Then I'm going to start here. X is about 0.36. Y is -1. I have a vertical stretch by a factor of 7/4. So my y value is -1. I multiply that by 7/4. That gives me 7/4, which is 1 3/4. So I'm about right there. I reflect in the y-axis, so I'm about right here. And then I translate down 1, 2, 3. So then I start at 1, 0. Vertical stretch, factor of 7/4, so 0 times 7/4 is 0. Reflect in the y-axis, translate down 1, 2, 3. When x is about 2.7, y is 1. Vertical stretch by a factor of 7/4, so 1 times 7/4 is 7/4, which is about 1 3/4. Reflect in the y-axis, so I end up over here, and translate down 1, 2, 3. So what I am missing is my x-intercept. So that's when y is 0. So 0 equals 7/4 times the natural log of -x minus 3. So that means that 3 equals 7/4 times the natural log of -x. Multiply by 4/7. That's going to give me 12/7. Hang on, I don't want the equals there. 12/7 equals the natural log of -x. I rewrite that in exponential form. So e to the 12/7 power equals -x, which means x equals -e to the 12/7 power. So -e to the 12/7 power, comma 0. All right. So I don't expect you to have a great estimation of that, but 12/7 is going to be a little bit less than 2. E is a little bit less than 3, so it's less than 9, obviously. Greater than 4, it's about 5 something actually, but you're not even going to know where to guess for that, and that's fine. If it's a funky number like that, I don't expect you to graph it. It's actually about 5.5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Not something I'd expect you to know, but that's where it is. I'll just tell you. So then when I graph this in, looks something like that. My domain goes from -infinity to 0. Range is -infinity to infinity. Increasing, not at all. Decreasing, -infinity to 0. As x approaches infinity, or as x gets as big as it possibly can, y is approaching -infinity. And as x approaches -infinity, f of x approaches infinity. Okay? Good? All right, so on the next section, you're just rewriting. That's all it's asking you to do. You're not having to solve for anything. Most of y'all did okay on the assignment on this. Some people, you got kind of everything backwards. Your base is 3 here. So the base of the log is the base of the exponential. So the base is 3. This is the power. So 3 to the 4th power equals 81. Goes in a little circle. 3 to the 4th equals 81. Here is 1/2. -5th equals 32. But when you have a fraction, it has to be in parentheses. Otherwise, you're only taking that 1 to the -5th power. Here the base is e, so e to the 2.08 power is equal to 8. So then I can take the exponentials and write them in log form. The base of the exponential is the base of the log. So this is log base 4. So that's my base of 128. Goes in a little circle again. Log base 4 of 128 is equal to 7/2. This base is e. So here's a lot of things I saw that was not good. Log base e. Although that's a true statement, we don't write it like that. You also don't write it like this. It's just the natural log. So the log base e is the natural log of 54.6, and that equals 4. Then here, same thing. The base is 10, so log base 10 is just the log of 10,000, and that's equal to 4. Okay. All right. So now I'm evaluating, and I use the change of base formula when necessary. That when necessary thing right there is important. Oh, that is black. That doesn't do any good. When necessary. Right. So that doesn't mean I use that on every single one of them, because remember, you're not going to get a calculator on the test, so you need to be able to solve them when you can. So we need to try all of them. Set that equal to x. So that means I would get 4 to the x power equals 1. If I can solve this getting a common base, then that's what I need to do. And I can do that. I can use a common base of 4. So 4 to the x power is equal to 4 to the 0 power, because 1 is 4 to the 0 power. So since I have this, I can use the 1-to-1 property, which means that x equals 0. Then here, I'll set that equal to x. So I get 1/5 to the x power equals 625. So I can get a common base here of, I'll use 1/5. 1/5 to the x equals, well, 625. 5 times 5 is 25, times 5 is 125, times 5 is 625. So this would be 1/5, but it needs to be to the negative, so I can get that in the denominator and be -4th power. So x equals -4. All right, so here, if I set this equal to x, then 12 to the x power equals 6. So this is a true statement, but I cannot get a common base here because there's not anything I can get to either one of these to make a power that'll work, which means this is one that would require the change of base. So that means that the log of 6 over the log of 12 is my answer. And we just leave it like that. So then this next one, this would be 8 to the x power equals 61. Well, again, I can't get a common base there, so this is just change of base. Log of 61 over the log of 8. And that's it. Okay. So now I'm going to condense these. Your rules for condensing and expanding and whatnot are all on that hot pink piece of paper that should be in your ISN. So the first thing I can do here is to get these numbers that are out here up into the exponents. That only works with a log. I saw some people trying to do that with ease today, and that does not make any sense. You don't get to apply it to everything. So this becomes log base 3 of x to the 4th power minus 2, I'm trying to make that an exponent, minus log base 3 of y to the 2nd power. So when I'm subtracting two logs with the same base, then I can change that to a single log that's division. This is not the change of base. This is a single log. So log base 3 of x to the 4th divided by y squared. And that is my single log. So on this one, before I take and do anything with that 1/3, I need to condense the inside. So the first thing I can do here, and you can combine some of these steps. I'm just going to probably write out more just so that I don't lose anybody. I get 1/3 to the times log base 7 of 64 plus log base 7 of 27 squared. Now, if you've actually worked this on your own, I would imagine some of you went ahead and you squared 27, and then when you condensed it, you multiplied 64 times whatever god-awful number you got from that, and then you, I don't know what you did, but if you don't have a calculator, all of that is a bad idea. So before you start just multiplying things, I'm just going to kind of leave things as they are for right now as I condense them. I have two logs with the same base that I'm adding, which means I can have a single log where I multiply the arguments there. So 1/3 times log base 7 of 64 times 27 squared. Okay, and I'm going to leave it just like that for right now. Then that 1/3 becomes an exponent. So now that's going to become log base 7 times 64. I'm sorry, not times. Log base 7 of 64 times 27 squared to the 1/3 power. So now I can use the power to a power and distribute that. And that becomes log base 7 of 64 to the 1/3 power times 27 to the 2/3 power. Now, as much as you might not like rational exponents, this is so way better than getting those ginormous numbers that you're not going to know what to do with. You should be able to take the cube root of 64. So this is log base 7. Cube root of 64 is 4. Then I need to take the cube root of 27, which is 3, and square it, which is going to give me 9. So this is just log base 7 of 36. And combining some of those steps is fine, but again, I wanted to make sure everybody knew where everything was coming from. Okay, good. All right, so again, working from the inside out. So I'm going to take care of what's going on first in here before I worry about that 1/2. I'm going to get 1/2, and I'm actually going to do a couple steps together. I'm going to move the 5 into the exponent on the k, and since I'm adding them two logs with the same base, I'm going to multiply these things, kind of do all that in one step. So it's going to give me 1/2 times the natural log of 64. Oh, that's a 4. Dang it. 64 times k to the 5th minus 4, well, I'll go ahead and make that exponent too, minus the natural log of m to the 4th. So then this 1/2 is going to become an exponent over here, so natural log of 64 times k to the 5th to the 1/2 power minus the natural log of m to the 4th. So when I do this and I distribute that 1/2 power to both of these, that means I'm going to take the square root of 64. So let me get the natural log of 8. I don't need parentheses there anymore. natural log of 8 times k to the 5/2 power minus the natural log of m to the 4th. Then I am subtracting two logs with the same base, so this is going to be the natural log of 8 times k to the 5/2 power over m to the 4th. I'm going to rewrite that part there. It's the natural log of that. That is my answer. All right, so to condense this one here, I'm going to put this exponent up here, and this is going to give me the log of x minus 4 squared plus the log of 3x. So this is being added, so these two things are going to get multiplied together when I condense them. But I'm going to go ahead and when I rewrite this, I'm going to put this 3x first. And then I'm going to go ahead and square this out. So this gives me x squared minus 8x plus 16. Okay. So I've multiplied those two things together, and I just went ahead and multiplied that out. Then I need to distribute that, so that's going to get the log of 3x cubed minus 24x squared plus 48x. And these parentheses here are very important. If they don't exist, then you're only taking the log of that first term. And that is my condensed into one logarithm. So now we're going to do the reverse of that and expand them. So anytime I have the root, I want to change that to a fractional exponent. So this would be log base 2 of 4x minus 5 to the 1/3 power. So that exponent gets to come out front. So I get 1/3 times log base 2 of 4x minus 5. These parentheses are very important as well. And I can't do anything else. I don't get to expand this into addition because it's minus 5. If it was just 4x, that's different, but that's the best I can do there. So on number 22, I had somebody ask me, how many steps can I skip? And I mean, pretty much you can just write down the answer if you know how to do that. If you need to do it in steps, that's fine too. But you've got things being multiplied and divided, and you've got to be careful skipping all of the steps all the time, because sometimes you think you can when you really can't. But I'll just go ahead and show you how you can do this. You've got 3 things being multiplied here. Now you got to be able to identify that. So I'm going to have 3 terms that are going to be added together, and then that one and one's going to be subtracted. So I'm going to start with log base 4 of 3 plus, and then when I do this a to the 7th, that exponent gets to come out. So I'm going to have 7 log base 4 of a plus log base 4 of c minus log base 4 of 5. Now I'm not saying you should always skip a bunch of steps, but the more you understand it, the less work you have to do writing it all out. And a lot of times in your notes, I'll write out more than what I might expect you to write out, just so that I don't lose you, and so that when you go back, you know where things came from and it doesn't look like magic. Because unfortunately, a lot of you seem to just write things out like they're magic when you're working them. And I don't think you understand where it's coming from. All right, so on 23, we got a couple of options. But I think the best thing to do is go ahead, Amy, you could bring the 3 out front here and then take care of everything on the inside and distribute, or you could go ahead and distribute that exponent, which might be a good idea. So this becomes log of 5 to the 3rd, and this square root is going to be 1/2, so that's u to the 3/2 over w to the 6th power. So it's just already all in there. And then as I take this apart again, I can go ahead and take it apart and put the exponents out in front. So I've got these two things being multiplied together and then one being divided, so there'll be a total of 3 terms in the end. So I'll have 3 times the log of 5 plus 3/2 times the log of u minus 6 times the log of w. Now on 24, when I go to expand this one, I don't get to, this subtraction here doesn't do anything. There's no rules for that. It's the log of things being multiplied that gets to turn into addition and subtraction, or multiplied and divided. So in order to be able to expand it, I have to have things in here that are multiplied or divided. So I need to factor this. So I'll run, even though I said I would never do it again, I will run through the whole factoring by grouping concept here. If I multiply 3 times -8, I get -24. So any two numbers are going to multiply to give me a -24, which means the signs are different. And then they have to add to give me this -2, or subtract, basically. So that's going to be 6 and 4. So I get 3x squared minus 6x plus 4x minus 8. Then I can factor out of these first two terms, 3x, and that'll be x minus 2. And then I can factor out a 2. And that leaves me with x, I'm sorry, not a 2, a 4, dang it. Factor out a 4, and that leaves me with x minus 2. So that means that 3x plus 4 times x minus 2 is what I get when it's factored. So this actually equals the natural log of 3x plus 4 times x minus 2, which means when I separate it into two that are added, I get the natural log of 3x plus 4 plus the natural log of x minus 2. And that's the best I can do with the expansion.